early sort of great successes of chemical engineering was coming up with these staged operations to make separations really feasible. Sometimes we don't appreciate what the people 100 years ago, what they figured out. It was pretty clever with these staged operations. There are typical assumptions you make, like constant Mollal overflow for the constant relative volatility between trays. One other that the heat of vaporization is roughly the same for both species, etc., etc. There are various operations. And if we try to model it in this class, for each tray, we try to make a block diagram and then hook them together. So you try for each tray to make a block diagram, and then you hook them together. They don't really give you an example in the book, but it's not more, for each tray, it's not more complicated than what we've done already. Then you could put them together. I'll leave that as a homework problem. What else is there? The next topic in the textbook is multiple input-output systems, which don't ask me why they bring it here. We did that before the first exam. In fact, I had a question on that on the first exam, where you have, for example, a CSTR, where you could have a change in the input flow rate as well as a change in the input concentration. And just to remind you, we were able to show, let's erase a little bit. So if you remember when we had a CSTR, when we finally did this, we had ECA prime tilde T plus some coefficient CA, so I could have A was the product. 1 over T was equal to something times B prime plus something else times CA prime. And we calculated that both on the first exam and also in class. And I'm not going to bother writing down or re-deriving what those coefficients are. And what we said is, obviously, if you take the Laplace transform, we have CA prime tilde times 1 plus st over t. So here I'll get an s, and here I'll get 1 over t, is equal to this thing times v prime tilde plus this thing times ca in prime. Or ca prime tilde is equal to this thing times t over 1 plus st v prime tilde plus this thing times t over 1 plus st ca in prime tilde. And when you invert, so this was just some sort of constant. These were just some sorts of constants. And what we were saying here is that the change, or as you see it here, the change in CA, when I've linearized everything, I had to linearize at a V prime tilde was due to the change in the flow rate, inlet flow rate, as well as due to the change in the inlet concentration. And when the systems are linear, they add. They add. That if I consider a fully nonlinear system, they wouldn't add. But in a linearized system, they add. And they can happen at the same time or at different times. So, for example, if V happens and CA in T. If this happens at T1, and this happens at T2, then for this regime, here, there's no change for t between T1 and T2. And here there's no change in v prime for t greater than T2. But here v changes at T1, and here CA in changes for T2. So if you remember, if these are step changes, v prime tilde would be delta v over s. CA prime tilde would be delta CA over s. And then I'm inverting over S, 1 plus ST, which, if you look at your table, that's the situation, line 5, for A equals 0, and that just gives me 1 minus e to the minus t over t. 1 minus e to the minus t over t. So what that tells me is my response to the first change is going to give me something times 1 minus e to the minus t over t, where t is t minus t1 over t. And this is for t between t1 and t2. And for t greater than t2, I'm going to have a 1 minus e to the minus t minus t2 over t. And I want you to notice, and this is for t greater than t2, and of course it's multiplied by a coefficient. And I want you to notice, as I've stressed a number of times this semester, that the time constant, t, is dependent on the system and not on the disturbance. These are the forcing disturbances. So notice the time constant for this change and for this change are the same, even though this was a change in V and this was a change in CA. They both relax at the same time constant. But notice that this is for the regime t greater than t1 less than t2. And this is the regime t greater than t2. So if I were to plot it, here's t1, here's t2. CA, and let's say everything was fine until here, and then I have some sort of change in delta V that makes CA go up, and then I have another change in, and this may not yet be at steady state, but in T2, I have another change that makes this thing go down, and eventually reach steady state. So here I have the part from T1 to T2, and here I have a part greater than T2. Here's where I get a delta V, and here's where I get a delta CA. So is that clear what's going on? If both of these happen at the same time, if T1 equals T2, then you're going to have your CA in, a CA prime of T. It's going to be equal to something plus something times 1 minus e to the minus t over t, plus something else times 1 minus e to the minus t over t, where this is the contribution, the coefficient for t minus t1 over t, and this is t minus t1 over t, where this is the coefficient for the delta v, and this is the coefficient for the delta CA. So if they happen at the same time, if T1 equals T2, then you just add these two. And of course, you have to see, depending on how big the coefficient is, if this coefficient is bigger than this coefficient, then it goes up. And if this coefficient is bigger than this coefficient, it goes down. Because I can factor this out. So that's sort of just sort of like a quick review, but this concept, this whole concept of how to do things is exactly what we had before the first exam. For some reason they throw it in here as if this were something new. It's not. Are there any questions on that? And just to remind you what these coefficients are, this we call Kp for Ca, and this we call Kp for V. So the coefficient here, here the coefficient was Kp for V, delta V, and here the coefficient was Kp for Ca times delta Ca. And since this is prime, I can need that. So this is Kp for V, delta V, and this is Kp for Ca times delta Ca. Yeah. So there I filled in what those coefficients are, where the Kp's or things are the steady state values. Are there any questions on that? I didn't really want to belabor that because it's something we've done before. Okay, so this sort of completes all of the preliminaries. So if you like, I shouldn't use the word, but a lot of times when you take a class, there are prerequisites that you need for the class. So before you come into the class, you have to complete all the prerequisites. The prerequisites for doing control is to know how to write down an unsteady model and how to analyze it. Unfortunately, those prerequisites didn't come in other classes. So the first, even though the title of this class is process control, the prerequisites for doing process control is what we had to do in the first half of the semester, what we did until now. So now we're done with the prerequisites. What does that mean? The first thing it means is that before we go on to the control part, there'll be an exam that, remember, the first exam was how you write down an unsteady model and how you solve it using methods of ordinary differential equations. What we've done since then is we said, that's too hard, particularly when you get to difficult systems, so we're going to come up with another method, the method of Laplace transform. So we came up with a method of analyzing the models we derived earlier, the first order models, either naturally first order or ones that we've linearized. And we came up with a method for solving those equations using Laplace transform methods. And then what we did is we said, most of the time that you don't need all that information. Most of the time there's a set of questions you want to answer and you don't even have to invert to do them. So stability at infinite time, you can do that without inversion. You've got a final value theorem, and you have the analysis based on the roots of the denominator, the zeros of the denominator, that tells you everything you need to know about stability. Then we also say, well, what happens if you have a sine or a cosine input? If you have oscillatory inputs? And we said that we can get all the information we want also without the inversion. We can get the frequency of the output is the same as the frequency of the input. We can get the amplitude ratio, and we can also get, let's see, we have the amplitude ratio, and then we also have the, what was the third thing? The frequency, the amplitude ratio, and
Phasing?
And the phase lag. We have all those we can get directly from the Laplace transform. So we thought, great. And then we examined some canonical systems using these tools. And we got some intuition into how interacting systems work, how non-interacting systems work, easy. And then earlier today, how interacting systems work, less easy. Still doable, but less easy. And we saw that they're more sluggish, among other things. Finally, we looked at parallel structures, where we saw with parallel structures, the infinite time isn't always enough information. We can get this overshoot or inverse behavior, and if that could lead to problems, and we can recognize that when we have numerators that are polynomials. Those only affect the coefficients, but still, they can give me overshoot. If that's a problem, I really need to do the inverse to figure that out. And we also spent a fair amount of time coming up with block diagrams, because block diagrams are very intuitive. They're very intuitive. They're much more intuitive than writing down a bunch of algebraic equations. Sometimes diagrams make your life a lot easier. So that was what we did here, and all that is fodder for exam 2. Well, now we're going to talk about feedback control. So we're going to start the new material for beyond the second exam. Let's just note, again, I'm going to be away next week, and what I'm likely going to do is we'll have a Zoom class next Wednesday. Because as I saw today, when we have an extra class, 90% of the class doesn't show up. A few of those people work, and the rest of them just don't show up. So next week, even though I prefer not to do Zoom, we will do a Zoom class for next Wednesday. Next Monday, we already made up that class today. I will also give you more homework so that you get the homework back, hopefully sometime, well, it'll be due sometime that, probably the beginning of the following week, and the week after next, the week when I come back, is likely when we'll have the exam, I would imagine 2 weeks from today. That's the most likely time for the exam, just to give you a heads up. Questions? So now we're ready for feedback control. What we've all been waiting for.
Switch it so that it's less glare on
So
the
excited to see feedback control, you're finally going to start seeing. So there are still some preliminaries. That is, until now we just did the prerequisites, and now we want to do the feedback control. So let me just draw a little diagram.